That's it. So now we need to talk about arrays again, and this time about something which is called resizable or dynamic arrays. Okay, so what happens if I'm adding an element to an array and the array is already full? So some bad things will happen, such as in Java, you will get array index out of bound exception if you try to add at the end. In Python, you will get list index out of range. Very good things actually, because in C, you will get no warnings. It will go past the end of the array and erase everything in your memory completely. So you would not even know why your program suddenly starts behaving really strange, because it will just go there, like whatever. You say your array has 100 elements, but you want to add at position 100, at position 101, 102, and it will go there and erase everything. And there could be something else stored in these memory addresses, and it doesn't care. So that's even much worse. So all of this is bad when we see such reference. Okay, however, when we start our program, we not always know how many elements to allocate. We don't always know that. So in advance, right? It can happen that now I need to store more elements than I originally thought, right? Let's say I'm collecting something from the user and it grows and grows and grows. I need to be able to resize an array. So this new data structure, new in a sense like it's variation of an old one, which is called dynamic array, also known as resizable array. The idea is like this: store in variable A an address of a given array, and when you need it, create a new array double the size of the original array, copy all the elements from the old array to a new array, and reset this address to the new double-sized array. Okay, so definition: dynamic array, it's a data structure that supports the same operations as a regular array, but does not limit the number of elements that it can hold. So see, this how it could be done in Java, for example. So see, here we have my array stores the position of the array in memory. That stores the position of the array of size 100 in memory. That's the address of it. So now let's say I'm adding. Now I need to add one more element, 101 element. Doesn't fit. So what I do, I create a new array of size 200 first. See, I create this new array, and this is its address, stored in the variable new array address. See, then I would copy, that's a special method, or you can do it in a loop. It's exactly the same efficiency, because you need to actually go and copy every element. You copy every element from here to here, right? And after that, you can reset this my array to point here. See, that's the only way to resize the array, because the array is by definition a contiguous place in memory of predefined constant size. So it cannot be resized at all. We just need to find another place in memory, double the size of the original. Then we need to copy everything which we already have into this memory, and then we will change our reference variable to point to this new place. So, okay, so then we would need to, like always in the array, we will keep the reference of the array in variable A. The capacity is the current number of slots that we allocated, and the size, the number of elements currently in the array. So that's how it works in the video or whatever, like how it's called, movie. Okay, so originally we have an array of size 2. We allocated only 2 spots. The size is equals 1 after we added A, and the capacity is 2. Now we added to B, size 2, capacity 2, all is good. Now we try to add C. There is no space in the array. So what we do, create a new array, and we copy AB into it, create a new array, double size, and reset A to point to this new array. So now we add C and D and E, and when we need to add E, then we will double the array, as you see, it was like capacity 4, new array, capacity 8. Okay. So why do we need to double? I now show you why do we double and not adding 1? Because if I every time I need to I need more space, I will add 1 and copy everything. That will be very expensive. That would need that almost every operation I would need to copy n elements. But if I'm doubling, there is something interesting happens here, something interesting. Sometimes, so we now will talk about a very important concept, which is called amortized analysis, right? Sometimes looking at the individual worst case may be too severe. So what is going to be the worst case of adding element at the end of the dynamic array? The worst case is when it's full and we need to copy n elements into a new space. That means worst case running time of adding element at the end of the array, of this array, which can change its size, is big O of n, see? But that is too severe because many, after we double the size, there is some space where each addition takes big O of 1. Many O1 operations followed by one big copy, see? So what is the total cost of inserting n elements? This total cost of inserting not one element, but n elements is called amortized cost, the amortization per operation, right? So we will count what is the total cost for n operations, and we will divide it by n. This is the definition of amortized cost. Given many like n operations, the amortized cost of each operation, basically average cost per operation, is going to be cost of n operations together divided by the number of operations, right? So that's kind of average cost of each operation. Okay, so intuitively, this cost, that amortized cost, should still be 1. That's intuition. Say we originally have k elements in the array, and the array is half full. K elements and it's half full. Then that means I can add another k elements. And each addition will take time O1 because it's half. Half k spots are still free. So in total, I will have k steps per k elements. Now I need to resize by copying 2k elements in time 2k, which is okay again, right? So in total, adding k new elements took OK plus OK, which is OK. See, we ignore the constants, right? 2 of OK. So that means per each of k elements, it's big O of 1. See, to add k elements takes big O of k. That means on average per operation, it's big O of 1. So this is a proof, more formal proof of this idea. Let's start with the array of size 1. If we choose a strategy of doubling the size of the array every time we resize it, then during the insertion of n elements, we will double and copy in total that many elements, right? First, we will copy 2 elements, then we will copy 4 elements, then we copy 8 elements, and up to n over 2 elements, right? Because that's now the final array is of size n, and we only created it because n over 2 was full. So we just copied n over 2 elements in order to add these elements. So in total, we will perform copy only when size is a power of 2. And I'm claiming that we will copy that log n times. The total number when we copy in order to insert n elements is going to be log n. Why is that? Right, because that's exactly like we did in these loops, right? To going with 1 from 1 to n, each time doubling. That will take log n steps. So the total number of times that I double array and copy is going to be log n. Do you agree? This sequence contains log n elements. That's what I'm trying to say. And now if you look at this sequence, can you see something about that sequence? Do you recognize this sequence or not? Remember, we were talking about sequences, like important summations. What is it? Arithmetic series? Not really, right? Do you see what it is?
Geometric.
It's geometric series, right? like we start with 1 and every next element is doubled. It's a geometric series with first element 1 and D